All right, welcome back to another lecture. We're going to cover the normal distribution in this lecture, right? So this is section 2.6. So make sure that you have those notes out and ready to go and that you're ready to dig in. And let's get into it, right? So in the previous section, 2.5, we talked about the normal distribution, right? Which was a particular kind of probability, right? There are certain kinds of probabilities that occur so frequently that they get special names. The binomial was one of those, and the normal distribution is another one. Okay, it's kind of hard to give a strict definition for the normal random variable without talking about this really nasty function right here, right? Because this is how a normal variable is defined. So if x is a normal random variable, that's what RV stands for, random variable, and we'll talk in more detail about random variables in the next section, just kind of generally, but if x is a normal random variable with mean mu and standard deviation sigma, then this is its PDF. The graph of this function is symmetric and bell-shaped. And if you don't believe me, what you could do is try to type this into the graphing calculator in Desmos ever so carefully, and you'll see that it's a bell-shaped distribution. So one thing that I want to point out looking at this PDF is that mu and sigma both show up in the function, right? So mu and sigma are going to have an effect on the way that the graph looks. And in particular, this is the effect that they end up having. Let me erase this. But in particular, this is the effect that they end up having. So for as far as mu is concerned, mu is going to shift the graph around. So here we have a distribution where mu is equal to 0, and then here we have a distribution where mu is equal to 3. And so you can see that the whole thing shifted shifted to the right by 3 units. What sigma is going to do is it's going to affect how spread out the distribution is. And neither of these facts is particularly surprising to us, right? Because we know that the mean is the center of the distribution. So, of course, if the mean increases, it's going to move the distribution to the right. And we know that the standard deviation measures how spread out the data are. So if you have a smaller standard deviation, then you're going to get this really kind of bunched up distribution like this one here. And if you have a smaller standard deviation, then you're going to have a more spread out distribution like this one here. So really the normal distribution is just the same old bell-shaped distribution that we've been talking about, but it's an important one because a lot of real-world data end up following a normal distribution, right? Things like height, birth weight, IQ, etc. And that should make some sense to you because whenever you're measuring something, it's usually going to be the case that most individuals are going to be close to average, and that there are going to be fewer individuals that are high above average and few individuals that are high below average. And so you're going to tend to end up with these kind of bell-shaped looking things for a lot of real world phenomena. What we would like to be able to do is compute probabilities involving the normal distribution. Now, the normal distribution is a type of distribution that we call continuous, right? And that's not a new word to you, but there are all kinds of continuous distributions, and the normal distribution is one of those. For continuous distributions, we use the probability density function of the distribution to find the probability that x is within a certain interval. In other words, we would have to use this function right here to compute probabilities. And the way that we compute those probabilities is we do a calculus problem, okay? So we're not actually going to do this by hand because most of you don't know calculus, right? Which is fine. But for those of you who do know calculus, this is what the calculation would be, okay? So the probability that x is between a and b is the integral from a to b of the probability density function for a normal random variable. So again, we're not going to actually do that by hand in this class, But, one thing I would point out is that even if you did know calculus, man, this would be a nasty calculation to have to perform. So we're just going to use technology to compute these probabilities. But here's what I do want you to walk away understanding. The probability that x is between a and b is equal to the area between A and B, right? It's this shaded area right here. This is the probability that x is between A and B. And this is true for any continuous function, right? So in particular, this is going to be true for a normal distribution, right? The probability that x is between A and B is equivalent to the area underneath the graph of the PDF, right? Between the x-axis and the graph of the PDF, between A and B. Immediately, there's kind of an interesting thing about continuous distributions like the normal distribution, and that is that the probability of observing any particular value is always going to be 0, right? The probability that x equals a is always 0, regardless of what a is. And we're going to talk about this in a little bit more detail in a second, but one reason to see why is because these probabilities have to be equivalent to areas. So if you're looking for the probability that x equals a, we would only be looking at this tiny little sliver, and that tiny little sliver is not going to have an area, or rather its area is going to be 0, right? The area of a one-dimensional thing is going to be 0 because there's no width to it, right? The area of a rectangle anyway is length times width, right? But if you don't have any width, then the area is just going to be 0. So the probability that x equals a is always 0 for any given number a. So that has some consequences when it comes time for us to compute probabilities in Desmos, and we'll talk about them as we come across them. But here's how we're going to compute normal probabilities in Desmos. So we're going to open up the graphing calculator in Desmos just like we did for the binomial distribution. But this time, instead of typing in binomial dist, we're going to type in normal dist because we're using the normal distribution. When you type in normal dist into the Desmos calculator, then you'll be prompted to enter something for the mean and standard deviation, and those will typically have to be given to you in the statement of the problem, unless you have some data, and we'll see some examples of that in this lecture as well. From there, if we want to compute a probability, we click on cumulative probability, and then we choose the type of probability that we want to compute. Just like with the binomial distribution, there aren't going to be options for us to compute strict inequalities, but in the case of a normal distribution, the probability that x is less than a is exactly equivalent to the probability that x is less than or equal to a. And that's different. That's different from the way it was with the binomial distribution. So again, this is something that we'll emphasize in a little bit more detail by looking at some examples here in a second. So let's get to it. Let's just look at some examples. Number 1 here says the weights of giraffes are approximately normally distributed with mean mu equals 2,200 pounds and standard deviation sigma equals 200 pounds. Compute the following probabilities and draw a picture of each. I'm not sure there's actually enough room to draw pictures of each of these, but we'll do our best. So for part A, we want the probability that x is between 2,400 and 2,500. In other words, we want the probability that a giraffe weighs somewhere between 2,400 and 2,500 pounds. So just drawing a picture of this real quick, what you would do is give yourself a little normal distribution. Okay, just do your best. The mean of the distribution should be right in the center of the distribution, right? So in this case, the mean should be right about there, and we were told that the mean was 2,200. Okay, we were also told that a standard deviation is 200 pounds. So if I go up one standard deviation, I would be at 2,400 pounds. And if I go up another one, I would be at 2,600 pounds. And I could continue to label these. If I go in the left direction, one standard deviation below the mean would put me at 2,000, and 2 below would put me at 1,800. And I'm looking for the probability that a giraffe is between 2,400 and 2,500 pounds. That would be 2,400, and 2,500 is right in between 24 and 26, right? So that would be this area right here, right? So this is the area I'm looking for. So this is the probability, right, that I'm being asked to compute. So to compute that probability, we'll use the normal distribution, right? We'll go over to Desmos and we'll use normal dist. When we do that, we have to put in the mean, which we've said already was 2,200 pounds. And we have to put in the standard deviation, which we said was 200 pounds. And then from there, we're just going to type in the probability that we want to compute, which is this one. Okay, so let's head over to Desmos and calculate this number. Okay, so here in Desmos, we'll type in normal dist, and then we'll put in the mean, which we said was 2,200, and the standard deviation, which we said was 200. And then if I want to get a picture of the distribution itself, I can click on this little magnifying glass, and that'll zoom in. Notice that it's labeling this axis the way that we labeled it on our page, okay, which is kind of nice. And now if I want to compute the probability, I'll click on this little cumulative probability button. And I want the probability that x is between 2,400 and 2,500. And then it shades in that little portion of the graph that we shaded in on our paper a second ago and computes the probability for us, right? 0.092, or if I want more than 3 decimal places, I can click on that little down arrow and get as many decimal places as I want. So let's go to 4. We'll say 0.0918. So 0.0918. Okay. I won't make you draw the pictures on parts B or C, but go ahead and give the video a pause and see if you can compute those two probabilities. Here's my solution. So for part B, we're once again going to use the normal distribution. Now, you don't have to write this out every single time if you're doing problems where, if you're doing a bunch of problems in a row where these are the same and nothing's really changing about them, then you don't have to write out normal dist. But I'm just going to write it out just to make it absolutely clear. So we want the normal distribution. We want to compute the probability x is less than or equal to 2,100. And let's see what we get. Okay, so I'm using the same distribution, but this time I want a left. Okay, I want to choose a left distribution so that I can put in 2,100. And there we go, 0.3085 approximately. And for part C, I would use the same distribution, right? The normal distribution, and I'm just going to put in the probability that x is greater than or equal to 2,100. I think this is going to require me to use the right distribution. So I'm going to click on area to the right, and there we go, 0.6915 approximately. Okay, 0.6915, that should be a 5. Okay, so that's how we compute probabilities with the normal distribution. Let's sort of focus in on that strange thing about the probability that x equals some number always being 0. So with the binomial distribution, we can actually compute the probability that x is some particular value, right? Like the probability x equals 2. But with the normal distribution, this is kind of silly. And to see why, here's kind of the reasoning. We already talked about the area thing, But let me give you another explanation. Okay, with the normal distribution, the probability of observing one particular value is always 0 because the probability that x equals some number is going to be not necessarily 1, but because there may be more than one way for that to happen, but it's always going to be some finite number up in the numerator. Whereas in the denominator, it's going to be an infinitely large number because with a continuous distribution, x could be any value. It's not just restricted to whole numbers, right? So for example, if you're talking about the heights of individuals, okay, that would be a continuous variable. If heights are bell-shaped, then we would say that they are normally distributed, okay? So if you're looking for the probability that someone is exactly 63 inches tall, the probability that somebody is exactly 63 inches tall is going to be 0, because with a continuous variable like height, you can always measure to any desired level of accuracy. So the chance that somebody is exactly 63 inches is 0, because probably they're actually 62.9997 inches, or maybe they're 63.0154 inches or something like that, right? So the probability that they're exactly 63 is 0. But the probability that they're between 62.5 and 63.5, now that would actually have a non-zero answer, okay? So anyway, this is why for a continuous variable, like a normal variable, the probability that x equals a particular value is always going to be 0. This has downstream effects when we go to compute probabilities in Desmos, okay? Because unlike the binomial distribution, there's no correction necessary for the normal distribution, okay? So when we were dealing with the binomial, the probability, when we wanted to compute a probability like the probability x was strictly less than 4, we said that we had to make an adjustment, and the way that we would actually type that into the binomial distribution is we would type it in as the probability x is less than or equal to 3. Okay, so for a discrete variable like the binomial variable, the probability that x is less than 4 is the same thing as the probability that x is less than or equal to 3. Whereas for a normal distribution, okay, actually let me color code these so that it's easier to follow. Okay, so for a binomial, the probability that x is less than 4 is equal to the probability x is less than or equal to 3. But for a normal distribution, the probability that x is less than 4 is just exactly the same thing as the probability that x is less than or equal to 4. The reason that they're equivalent is because the probability that x equals 4 is 0. Okay, so that doesn't contribute anything to this probability. Okay, so the probability that x is less than or equal to 4 is just going to be the same as the probability that x is strictly less than 4, since the probability that x equals 4 doesn't contribute anything for a continuous variable like the normal. Okay, similarly, right, for a binomial distribution, the probability x is greater than 4 is equal to the probability x is greater than or equal to 5. Whereas for a normal distribution, no adjustment is necessary. Okay, for a normal distribution, the probability x is greater than 4 is just exactly the same thing as the probability that x is greater than or equal to 4. Okay. So here's kind of like the general rule, okay? For a binomial distribution, you have to make these adjustments. For a normal distribution, no adjustments are necessary. Okay, so this set of examples in example 2 is very similar to the examples that we did when we looked at the binomial distribution for example 4. Okay, so if I were you, I think it would be a very wise thing to do to take out your 2.5 notes and compare the work that we did for number 4 to the work that we're doing here for number 2 in this set of notes. And that'll help you to understand a little bit better what we're saying up here about with the binomial we have to make adjustments, but for the normal we do not. Okay, so let's get into this example. It says a pediatrician obtains the heights of her 203-year-old female patients. The heights are approximately normally distributed with mean 38.72 inches and standard deviation 3.17 inches. Determine the proportion of 3-year-old females that have a height, and then in part A, we want the height to be exactly 35 inches. Well, we're told that the heights are normally distributed, so we're going to use the normal distribution for this. Normal dist. When we use the normal dist, we have to put in something for the mean. We were told the mean was 38.72 in this case, and we have to put in something for the standard deviation. We were told the standard deviation was 3.17 in this case. Okay, and now we want to compute the probability that x is exactly equal to 35. Now, you may recall from our discussion of the binomial distribution that there actually isn't a way to put the probability that x equals 35. What we have to do is type it in this way, right? We'll say this is the probability that x is between 35 and 35, okay? But you also know that this is going to be 0, okay? Without even doing the work, you know that this is going to be 0 because for a normal probability, the probability that x equals some number is always going to be 0. But just to kind of verify that, let's go ahead and run over to Desmos and type that in. Okay, so we've got, actually, let me just get rid of this one. We've got normal dist 38.72, 3.17. I'm going to zoom in on that and then compute a probability. We wanted the probability that x was between, well, that x was equal to 35. So, right, so between 35 and 35. And sure enough, it's 0, right? It's 0. It's not even highlighting an area here because the width of this would be, well, there would be no width to it. So there's no way to show an area here, right? The area is just 0. Okay, let's look at part B. So we might not be able to compute the probability that x equals 35, but we can compute the probability, well, okay, let me rephrase that. We can compute the probability that x equals 35, it's just that it's 0, okay? But if we look at the probability that x is between 34.9 and 35.1, then we should get something non-zero there. And I'm still using the same normal distribution that I was using before. So here the only thing that changes is the probability that I'm trying to compute. So let's see what we get. So we want 34.9 and 35.1. And there you go. Now it's highlighting a little area for us, and it's telling us that, hey, that area is about 0.0126. Okay. Okay. Let's look at the next set of examples, right? Parts C and D. In part C, we want the probability that the female patient, the 3-year-old female patient, is at least 35 inches, at least 35. So again, I'm using the same normal distribution as before, but we want the probability that her height is at least 35. So that would mean 35 inches or more, okay? So greater than or equal to 35. So in Desmos, we're going to have to use a right region, right? So that we're doing greater than or equal to 35. And that looks like it's about 0.8797. All right. Well, now let's come to part D. It says we want the probability that she's more than 35 inches tall, right? So we want the probability now that x is strictly greater than 35 inches tall. And if this were, so I'm going to write something incorrect, so don't write down what I'm about to write down. If this were a binomial probability, then we would say that this equals the probability that x is greater than or equal to 36. Okay? But this is not a binomial probability, this is a normal probability, so no adjustment is necessary, right? It's just going to be 35 still, okay? So this is going to be exactly the same as what we just computed, 0.8797. Okay, so for a normal distribution, as well as just for any continuous distribution, parts C and D are exactly the same thing. Okay, with that in mind, go ahead and pause the video and try out parts E and F on your own. Here are my solutions, right? The probability that x is at most 37, that means that 37 is the upper limit, right? X has to be less than or equal to that. So that's going to require me to use a left region and a 37 in that place. So that comes out to about 0.2937. Okay. For part F, we want the probability that x is strictly less than 37. Okay. And once again, I'm going to write something incorrect, so don't write this down. If this were a binomial probability, then we would say, okay, we need to make this adjustment, right? The probability x is less than 37 is the probability that x is less than or equal to 36. Okay, that would be true for a binomial. But for a normal, we don't need to make any adjustments, right? We'll leave this at 37. Okay, they're exactly equivalent, which means our answer to part F is the same as our answer to part E. Okay, and that's it, right? That's all there is to computing normal probabilities. We do have one last topic to cover here in this section, and that's the shape, center, and spread of the normal distribution. But this should be fairly straightforward. Okay, so as far as the shape is concerned, the normal distribution is always bell-shaped. That's sort of its defining characteristic, okay? It's a bell-shaped distribution. The center of the distribution, surprise, surprise, is just going to be the mean, okay? So mu sub x, that is the mean of our random variable x, is equal to the mean of the distribution. So intuitively, that's just like super obvious, right? But we can also prove it mathematically, and I'll give a link to a video of a proof in section 2.7, okay, in the next section. What I also do want to emphasize here, though, is that this is also the expected value of the distribution, okay? So the expected value is the mean. If you're told, the average IQ score is, I don't even know what the average IQ score is, 100, I think. I think it's like 100 is meant to be the average. So if you're told the average IQ score is 100 with a standard deviation of 15, what if you randomly choose somebody, what IQ do you expect them to have, right? What's the expected value? You would say, well, it's 100, right? Because the mean is the same thing as the expected value. Similarly, the standard deviation of our random variable x is equal to the standard deviation of the distribution. And again, a proof will be given in section 2.7, but hopefully it's just intuitively obvious that that would be the case. So let's take a look at at one last example. Okay, this time we have some data. It says the following data represent the speeds in miles per hour of 16 randomly selected vehicles traveling down a state highway. Part A says use art of stat to compute the sample mean and sample standard deviation of the data. Okay, so it's been a while since we've done that, but we can do that. Shouldn't be too hard. And then it says, assuming that these statistics are good approximation for the population mean and standard deviation, if another car came traveling down this highway, how fast would you expect it to be going? Okay, Well, the expected value is the same thing as the mean. So once I have the sample mean, I should be able to answer that second question. So let's go ahead and try to get the sample mean. So I'm going to go over to Art of Stat. I'm going to open up the Explore Quantitative Data app. And let's do our own. It's been a minute since we've used Art of Stat, right? But I'm going to go ahead and enter my own data, and I'm just going to do this by brute force. There might be an Excel spreadsheet that has the data in it in the lecture description already. So if so, feel free to just go ahead and copy and paste from there. But I'm just going to do this the old-fashioned way for now. Okay. So once you get all the data in there, however you choose to get it in there, you should end up with something that looks like this. Notice right off the bat that this looks like a pretty symmetric distribution. It looks fairly bell-shaped. It's not perfect, but it's close, right? It's a pretty nicely bell-shaped distribution. And here are the mean and standard deviation, of course, right? So this is what we came for. Let's just round to one decimal place. So we'll call this 60.6 and 5.4. So x bar is about 60.6 and s is about 5.4. Okay. Now, we're told to assume that these statistics, right, right here are good approximations for the population mean and population standard deviation. In other words, we're meant to assume that mu is, pretty much 60.6 and that sigma is pretty much 5.4. Okay? Operating under that assumption, we're asked, how fast would you expect the car to be going, right? If another car came barreling down the highway, how fast would you expect it to be going? Well, the expected value is the same thing as the mean. And the mean is approximately 60.6. So that would be the answer to that question, okay? Now part B says using the values that you computed in part A as approximations for mu and sigma, okay, so we're assuming this. It says compute the probability that a car would be traveling down this highway at a speed faster than 57 miles per hour. Okay. Well, remember how I said a second ago that the distribution looks bell-shaped? Let's pull it up again. I ran out of time. Whatever. It was a bell-shaped distribution. Actually, you can still see it here, right? So it's a bell-shaped distribution. So because it's bell-shaped, we can go ahead and use the normal distribution to compute this probability. So normal dist. And we're assuming that mu is approximately the same as the sample mean that we computed. We're assuming that sigma is approximately the same as the sample standard deviation we computed, okay? And now we want the probability that a car will be coming down this highway faster than 57 miles per hour. And of course, in Desmos, this is equivalent to saying that x is greater than or equal to 57. Let's see what we get. So I'm going to use normal dist with a mean of 60.6 and a standard deviation of, 5.4. Okay, let me zoom in on that distribution. And I want to compute the probability that x is greater than 57. So it looks like there's about a 75% chance of that happening, right? 0.7475. Okay. So there's a pretty good chance, right, that the car will be going faster than 57. All right, part C. Would it be unusual for a car to travel down this highway at a speed exceeding 51 miles per hour? Or what about 71 miles per hour? Well, what does it mean for something to be unusual? it depends on the definition you're using, right? But in this chapter, the definition that we've used is we've said that something is unusual if there's less than a 5% chance of it occurring. Or in other words, if its probability is less than 0.05. So I think what we should do is compute the probability that a car goes more than 51 miles per hour, and then compute the probability that a car goes more than 71 miles per hour. And if either of those probabilities is less than 0.05, we'll say that yes, those would be unusual observations. So I will let you give the video a pause and go ahead and try that out. Here's my solution. I'm using the same normal distribution that I used in part B, and we're going to look for the probability that x is greater than 51. We're also going to look for the probability that x is greater than 71. Okay, so let's head over and see what those values are. So I want the probability x is greater than 51. That's not unusual at all, right? That's almost, in fact, that's almost guaranteed. It's like 0.96. There's like over a 96% chance that this will happen. So 0.9623. Okay. All right. Well, so is that less than 0.05? No, obviously not. So this is not unusual. Actually, let me give my reason. Right? It's not unusual because it's more than 0.05. Right? So this is not unusual. Okay, what about 71? Let's see. 71 instead of 51. So that comes out to about 0.0271. Now that is less than 0.05, right? So this is unusual. Okay, so it would not be unusual for a car traveling down this highway to be going more than 51 miles per hour, but it would be unusual for it to be going more than 71 miles per hour. Okay, that'll do it for this section. Thank you for hanging in there, and we'll check in with you on the next one.